All right, hello everyone. Welcome to the video for chapter 2, lecture 2. So we'll finish up chapter 2 in this video. So if you guys remember last time, we got up to isotopes, right? Um, which are same number of protons but different number of neutrons, right? And then we did some example problems to determine AZ, right? From the AZX notation. So let's move on. We're gonna talk about ions now. So please have your periodic table out. Um, and we're gonna see, how it works when an element either lose or gain electrons. Okay, that's how they become ions, right? And there are two types of ions, okay? Positively charged ions are called cations, and negatively charged ions are called anions. Okay, so you should know those terminology. Okay. So atoms like to lose or gain electrons. A lot of atoms are reactive, so they don't just want to stay neutral. They either gain or lose electrons. And remember that electrons are negatively charged, right? So if you lose electrons, you lose a negative charge, and therefore you have a surplus of positive charge, meaning you become a cation. Okay. So when you lose electrons, you become positive. All right. Now, when you gain electrons, of course, since electrons are negative, right? If you gain a negative, you become negative, right? So you become an anion when electrons are being gained. Okay. The way I like to think about it, it's like life, right? If you lose negative things in your life, you become more positive, right? But if you gain negative things in your life, you become more negative, right? Okay, so let's talk about the periodic law and the periodic table. Yep, so please have your periodic table out. The way that it's arranged was in 1869, Mendeleev noticed that there were certain group of elements that had similar properties. And so he listed the elements. He found that when he listed the elements in order of increasing mass, these properties recurred in a periodic pattern. So that's why it's called the periodic table. So there's this repeating pattern where certain elements would behave similarly, right? Will have similar physical and chemical properties. So, here's an example, right? He would list from hydrogen to calcium, and he saw that, oh, lithium, sodium, and potassium, for example, have similar properties. So instead of the periodic table being like just long, right, horizontally, where he saw that they had recurring properties, he started a new line. So that's why lithium, sodium, and potassium now are in the same column, right? And so that's what we know now, is that elements that are in the same column will have similar chemical and physical properties. Okay. And that's going to be really helpful later on when you guys are like, trying to predict reactions, trying to predict what an element will do, right? Will it gain or lose electrons? It's really useful to look at the column, with respect to the noble gases. Okay, so keep that in mind. Similar properties fall into the same columns. So Mendeleev's table actually contained some gaps at the time, right? Because they didn't know all the elements. They just had, the existing ones. But he was so keen on his observations that he was able to predict undiscovered elements, right? He was able to predict their density. He was able to predict, how they react with oxygen, their melting points and boiling points. He was pretty good at predicting those. So, for example, he predicted the element which he called ecosilicon, which was later, named germanium when it was actually found by the German chemist Winkler. And germanium had the properties that Mendeleev predicted. So pretty remarkable um, Mendeleev just using the periodic law to predict, undiscovered elements. So now in the modern uh, periodic table that you guys look at, elements are listed in order of increasing the atomic number rather than increasing mass. It just works better that way. But it still looks very similar to Mendeleev's table. So he's, credited with, how your periodic table looks right now, right? And so when you pick up a periodic table, they all look something like this, right? And you can divide the big periodic table into these major three divisions. The metals, which are on the left side of the periodic table, right? Left lower side of the periodic table, in sort of in yellow here. And then in the green, that's the upper right, that's the nonmetals. Okay. And then you have these elements that border the metals and the nonmetals. They're called metalloids, meaning they're like metals, right? But they're not actually metals. So they take on properties between the metals and the nonmetals, right? So on your periodic table, if you want, you're not allowed to write anything on it, but you can color code, right? So if you want to color code, you want to draw this staircase a little bit stronger because you see the metalloids are the ones that are bordering this staircase, right? So that, you can have like a rough division of the periodic table as well, okay? Okay, so the rough classification, right? Metals, nonmetals, and metalloids. Let's go into more details about each of these division. So the metals are on the lower left side, and they all share some common properties. They're really good conductors of heat and electricity. They're malleable, which means they can, bend and be pounded into flat sheets. They're ductile, which means they can be drawn into wires. They're often shiny, right? We know that. And when they undergo chemical reaction, they tend to lose electrons. Okay, so meaning they tend to become cations, aka positive, right? So chromium, copper, strontium, lead, right, are typical metals. You guys have heard of those, right? Very, very shiny, malleable, ductile, right? And tend to lose electrons. Nonmetals, on the other hand, right, they are opposite of metals. They lie on the upper right side of the periodic table. There are a total of 17 nonmetals, right? 5 are solids at room temperature. So carbon, phosphorus, sulfur, selenium, and iodine are solids. Only 1 is a liquid, and that's bromine. And then 11 are gases at room temperature, right? So we know that the noble gas, right? Helium, neon, krypton, xenon, all the noble gases, and then also hydrogen, nitrogen, oxygen, fluorine, chlorine, um, uh, and then radon. Radon's a noble gas as well, right? So 11, 17 total, right? So you can say that on the periodic table, you have mainly metals, right? And also state of matter wise, mainly solids, right? At room temperature. So their properties tend to be opposite of metals, right? Poor conductors of heat and electricity, not ductile, not malleable, and they like to gain electrons when they undergo chemical changes, right? So that means they want to become negative, right? So gain electrons, become negative. So oxygen, carbon, sulfur, bromine, iodine, all those are considered nonmetals. All right, and then the metalloids, right? Those elements that are lying on that staircase or that zigzag, okay, they exhibit mixed properties, properties between those of metals and nonmetals, right? And so they are often classified as what we call semiconductors because of their intermediate electrical conductivity. Okay, so the periodic table can also be divided into the main group elements and the transition elements, okay? So you should know this division as well because I will be referring to that, right? Main group elements versus the transition elements or the transition metals. So where are those? The main group elements are on I call them the wings of the periodic table, right? So on the first 2 columns, and the last 6 columns are the main group elements, okay? And then in the middle, we call those the transition elements, okay? And there's something else you should notice, how they are numbered. So if we count, okay, you see these little numbers, 1, 2, right, 3, 4, 5, 6. We count all the way across. We have 18 columns on the periodic table. Okay. And then we have 1, 2, 3, 4, 5, 6, 7. Okay. And that's 7 rows. Okay. And there are terminologies for these. The columns are called groups, and the rows are called periods. Okay. So if I'm referring to period 3, then I'm talking about this row right here that starts with sodium. Okay. Now for the columns, you see that there are, two um, ways of numbering, right? You have just 1 through 18, but you also have the A's and the B's. The A's and the B's separate the main group, right? The main group get A behind the number, and then the transition elements get B. So that's the numbering I'm going to use, right? I'm going to be like group 6A. Group 6A is column 6A, okay? And that's the column that starts with oxygen, okay? Or if I say group 2A, then I mean the second column, right? That starts with beryllium, okay? So for main group elements, that's how I will refer to them, okay? So you should be used to, how I refer to these, right? How to number these. And so again, if I say period 5, now that means row, right? Period 5 starts with rubidium here, Rb, and goes all the way across. Right? All right. So, right, vertical column is group, horizontal row, period. There are a total of 18 groups and 7 periods. Okay, let's start with the noble gases. Okay, so some of these columns, since we know a lot about them, some of these columns, some of these groups get a name to them, right? So group 8A, that's the last column on your periodic table. Those are called the noble gases. Okay, and why are they called noble gases? Noble means they are unreactive. Okay, they're very stable, and they don't react. Okay, so things like helium, that's used in balloons, right? Very chemically stable. It does not combine with any other element. Okay, so you will still find helium in the atmosphere. Um, of course, helium's really light, so it's constantly being lost to space, but there's still some helium left in the atmosphere. And you'd find it in its elemental form because it's so stable, which is really rare, right? To find elements still in their elemental form, as old as we are, right? As old as the Earth is now. Okay, group 1A, you guys should know that this is called the alkali metals. Okay, and the alkali metals are all really reactive metals. Um, they like to react with water. And the reaction with water is really, really vigorous. Okay? Let me show you guys a cool video involving the reactivity of the alkaline metals in water.
Oh, hey. Yeah.
In air, the elements quickly become coated with compounds that form on the metal surface. Here, for example, is lithium. When we splice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkaline metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkaline metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a light flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkaline metal.
But of course, it's not just the air that they could react.
All right. So you guys can see that the group 1, right, alkaline metals are very reactive, particularly with air and water, right? So what happens to them is they get oxidized, which means they lose their one electron. Remember, metals like to lose electrons. So they like to lose their electrons to water, for example, and that creates hydrogen gas, which is very explosive, right? And as you go down the group and the atoms get bigger, later on you guys will know why that is, okay? But as they get bigger, they lose electrons more readily. And so that's what gives rise to the increase in activity of these alkaline metals, right? Okay, and then you guys should know group 2A is called the alkaline earth metals. Their reactivity is very similar to group 1A, but it's not as vigorous, okay? It's not as vigorous as the group 1A. And the reason is group 2A metals, they like to lose 2 electrons. Okay, and so in losing 2 electrons, they're slower at, losing electrons. They have to lose 2. And so the reaction is not as vigorous as in group 1A. Okay, now let's take a look at the halogens, right? So the halogens, group 7A, right next to the noble gases, right? These are actually all nonmetals. Okay, so fluorine, bromine, iodine, and astatine. Fluorine is a pale yellow gas. Chlorine, a greenish yellow gas. That's really pungent. So if you've been in a swimming pool, that's treated with chlorine, you can smell that, right? Bromine is a liquid, and iodine is a purple solid. So even though they're nonmetals, the halogens are quite varied, right, in as far as states of matter. Yeah. All right, so let's think about how ions form in the main group. So remember, we said metals, they tend to lose electrons to form cations, right, to form positive charges. Then the nonmetals, they tend to gain electrons, right? And since electrons are negative, you will form a negative charge. You form an anion, okay? And how you can tell how many electrons get lost or gain is to look at your periodic table and see, where the element is with respect to the noble gas. Okay, remember that we said the noble gas is very stable. And so everything, all reactions that happen, they try to get to the noble gas number of electrons, the noble gas electron configuration. Okay, so everybody tries to be like the noble gas because that's stable, right? So if you look at group 1A, okay, go ahead and look at group 1A in your periodic table. That's the first column. Okay, if you ask yourself, what is the easiest or quickest way to get to the noble gas? you have to go left, right? Because the noble gas is um, the last column, right? So you have to go left, and therefore losing one electron, right? So remember how the periodic table is set up. It increases by one proton as you go to the right and down, okay? So that means if you go back left one space, you're losing one electron, and therefore you become 1 plus, okay? So group 1A are 1 plus ions. How about group 2A then, right? So put your finger on the column, group 2A, and count the quickest way to the noble gas. You'll see that you want to go left again, right? You want to go left how many spaces? 2 to get to the noble gas. So that means you're losing 2 electrons, and group 2A will tend to form 2 plus ions. Okay, does that make sense? All right. Now, let's go to the right side of the periodic table, right? So the halogens. Group 7A is right next to the noble gas, right? And just one space to the right is the noble gas. So group 7A is going to want to go right, right? Going right, one space means gaining one electron, and so therefore you form a 1 minus ion. Okay. How about group 6A? Right? Put your finger on that. Group 6A, quickest way to the noble gas is right, 2 spaces. All right, so that's gaining 2 electrons, and therefore you will form 2 minus ions. Okay. So for the main group elements, you have pretty predictable charges, as you can see, right? All group 1A elements would tend to form 1 plus, group 2A 2 plus, group 7A 1 minus, group 6A 2 minus, right? But the transition elements, they form various different ions and charges. So we can't predict those, but here's the table in which, here's the ones that are shown are predictable. So you see that group 1A, 1 plus, group 2A, 2 plus, group 7A, 1 minus, group 6A, 2 minus, and even nitrogen, right? You can guess what charge it would be. Because it's in group 5A, well, it wants to go 3 spaces to the right, right? 1, 2, 3 to get to the noble gas, which means it wants to gain 3 electrons and therefore becomes 3 minus. Okay. Now, if you look at aluminum, right, and you ask the same question, it's the quickest way to the noble gas. Well, if you go right, you have to go right 5 spaces, don't you? 1, 2, 3, 4, 5. But if you go left, 1, 2, 3, that's shorter. So that's why aluminum will have the 3 plus, right? Because aluminum will want to lose 3 electrons, right? So this is really useful, guys. Okay, these predictable charges you should, use. That's how you should use your periodic table. That way you don't have to memorize these charges, right? You're going to do it by the position of these elements on the periodic table, and it's going to help you tremendously, later on when you are, forming chemical equations, chemical compounds, when you're doing reactions. Is going to be very helpful. Okay, so that's really how you use your periodic table. This is, one of the key things that you should be able to glean from your periodic table is the charge. All right. So let's do these problems. We just did aluminum, right? We just said the charge of aluminum would be 3 plus, right? So it wants us to predict the charge of these. So what about sulfur? Okay, I'll give you guys a second. Go ahead and look on your periodic table. So you see that sulfur is in group 6A, right? So group 6A is 2 spaces away from the noble gas, okay? And so it's going to want to gain, right? Because sulfur is to the left of the noble gas. So it's going to want to go right to get to the noble gas, 2 spaces. So you gain two electrons and therefore become 2 minus, all right? Okay, let's predict the charges for D. Let's keep going. Nitrogen, right? Okay, put your finger on nitrogen, look up at the group number. Okay, you'll see that it's 5A. Okay, so group 5A, you want to go to group 8A, that's 3 spaces to the right, which means gaining 3 electrons, and therefore nitrogen is 3 minus. Okay, all right, now look at rubidium. Okay, rubidium is in group 1A. Okay, quickest way to the noble gas is going left. You're going to go left 1 space. Okay, and so therefore it's going to be 1 plus. Okay, that means losing 1 electron is 1 plus. Okay, so now, again, look at your periodic table. You guys are going to see that there's a little number, okay, underneath each chemical symbol, right? These numbers denote what we call the atomic mass, which is the average mass of an element's atom, right? That's the mass of one atom in AMU, which remember is atomic mass unit, okay? So the atomic mass of each element, it's sometimes called atomic weight too, by the way. But the atomic mass is calculated by taking the average mass of the isotopes weighted accordingly to the natural abundance of each isotope. So it's a weighted average, okay? So here's an example of how we calculate this weighted average, okay? So let's take a look at chlorine, okay? You see that underneath chlorine, there's a number, right? 35.45. So I'm going to walk you through how that number is calculated. Well, chlorine has two naturally occurring isotopes. One is called chlorine 35, and it has a mass of 34.97 AMU, right? Close to 35. Its natural abundance is 75.77%, okay? And then we have a heavier chlorine, chlorine 37. Its mass is 36.97 AMU, right? But it's present in less abundance, 24.23%. So now we're asked to calculate its atomic mass, okay? So if we were to just do this as a simple average, okay? If we have a mass of 34.97 AMU and a mass of 36.97 AMU, and we're at, okay, if we just do the straight up average of chlorine, we would have 35, right? The number right in the middle. So the normal average would be 35.97. Okay. But you see, doing a normal average wouldn't make sense, right? Because the normal average doesn't reflect that most of chlorine is the heavier one. Okay. Um, we look at the abundance again, right? Go back and look at the abundance again. Sorry, most of the chlorine is actually the lighter one. Okay. So if you have 35.97, that's, that's not a good way to do it, right? Because you're not taking into account that the lighter chlorine 35 is present in more amount. And so that's why you have to do a weighted average instead of just a straight up average. Okay. So how do you do a weighted average? You take the percentage and you turn it into decimal. So you take 24.23 and you turn it into 0.2423 and you multiply it by 36.97 AMU, okay? And that's going to be equal to 8.9578, okay? Then you do the same thing to the other isotope. You take the percentage, turn it into a decimal, right? So meaning divide by 100 and you get 0.7577. And then you multiply by its mass, 34.97, and you get another number. Now, what do you do with those two numbers? You add them together to get the atomic mass of chlorine. Okay, so you compare this number to this just the straight up average. It's skewed more towards the lighter, right? The lighter isotope, which makes sense, right? Because the lighter isotope is present in a larger amount. So 35.45, that's how we get that number. All right. So in general, right, all you have to do is take the fraction of the isotope, okay, so the decimal form of the percentage, multiply by the mass of that isotope, and then do it for every isotope, and then sum it all together. So this sign right here, sigma, means summing it all together, okay? So that's all you gotta do. So it doesn't matter if you have, 2 isotopes, 5 isotopes, doesn't matter. You do the same thing, just a fraction of that one isotope times its mass. If there are 5 isotopes and you need to do, 5 of those, and then you just add them together, okay? So let's try it with the copper example here, okay? So copper has 2 naturally occurring isotopes. Okay, copper 63, which has a mass of 62 62.9291 AMU. And that abundance is 69.17%. Okay. And then we have a copper 65 with a mass of 64.9278 AMU. Okay. And the natural abundance of 30.83%. Okay. Now remember what we have to do to calculate the atomic mass, right? Weighted average, meaning turn the percentage to a decimal. So now this becomes 0.6917 times 62.9291, okay, and get a number there, right? So go ahead and calculate with me. Remember that you should also have, a calculator out. 62.9291 times 0.6917. 43.53. Okay, and notice why I'm using 4 sig figs here, right? Because of this number. Okay, and then the next one is going to be 0.3083 times 64.9278. So 20.02. Okay, and then we add those together, right? And we'll get 63.55. Right. And remember the when you're doing sig fig here, since we're adding, right, we go by fewest decimal place. So it's 2 decimal place, and that's why I round to 2 decimal place. Okay, so 63.55. AMU, don't forget the units. And now look on the periodic table, right? You'll see that certainly the atomic mass of copper is 63.55. Okay. So more examples here, right, that you can practice. So make sure you do that so you know how to calculate atomic mass. Okay. All right, let's talk about mass spectrometry. How do we determine the abundance, right? How do we as scientists know what the abundance of these isotopes are when we, find the elements in nature, okay? So that's the method. The method is called mass spectrometry, and the instrument used to measure that is called a mass spectrometer. So, when you go out into nature, right, and you bring a sample back of this element, what you do is you put the sample into a furnace, right? And the furnace is going to ionize. There's an electron beam that ionizes the sample, meaning it knocks an electron off of the element, and so it becomes charged, okay? And these charge particles now are passed through electrically charged plates to accelerate the particle. And then the particle goes through a magnetic field, which will deflect these charged particles and therefore separate them from lightest to heaviest particles. Okay, so there's a detector, right? And it'll separate them from the lightest to heaviest particles. The detector can also detect how much is there. So you'll get out um, a diagram like this, right? You get out the height of the isotope is basically its population, right? So you can see that chlorine 35, for example, is more abundant than chlorine 37, right? So it separates it out by mass. And now as far as percentages go, we can actually kind of eyeball this, right? We can ask like how many of the blue bars are going to go into the yellow bar. And if you eyeball it, it looks like 3, right? Because that's 1, 2, 3. So roughly 3. Okay. So what you have is a 3-to-1 ratio. Okay. So a 3-to-1 ratio then is What percentage? So ask yourself that. 3 to 1. What percentage is that? Okay. You have 4 pieces total. Okay, so that's how you calculate. 3 plus 1 is 4, right? So you have 4 pieces total, and the first is 3 out of 4. So what's your percentage? 75%, right? To 25%. Okay. Does that make sense, right? 3 to 1 is 75 to 25. And so if you guys look back at the previous example um, that we did for this isotope, you see, 75, 25 roughly, right? And so that's how these abundances get calculated or get measured using mass spectrometry. Okay. All right, let's go to the next example. So now we have silver, right? Again, 2 isotopes. We see that they're about equal, aren't they? Right? Silver 107 and silver 109, right? Ag silver. It's about equal. So what would you say then? About equal would be like 50-50, right? Or since Ag 107 is a little bit less than Ag 109, maybe you can say 48 and 52, right? 48% is silver 107, 52% is silver 109. Okay, so that's a good, estimate just by your eyeballs. But of course, these are all done by computers. So they're going to give you a very precise number for natural abundance, right? All right, guys. So the next topic we're gonna do is called the mole, and it's a review to you guys have heard of the mole before, um, but yeah, let's review it. What is it? The way I like to think about it is it's a chemist's dozen, right? And we know what a dozen is. It's a way to group objects, right? So in saying 12 eggs, right? We say 1 dozen eggs. Yeah. Just a way of grouping it together. So there we group things in many ways, right? So a duo would be like a group of 2. A trio is a group of 3, right? Or quartet is a group of 4, and so on and so forth, right? But the dozen, right, we use a lot. So we use that as an example. It's a chemist's dozen, right? So 1 dozen is 12 things. But in chemistry, because atoms are so small, right, the grouping is going to have to be a much larger number than 12. And what is that number? It's called Avogadro's number. And the grouping name is called the mole, right? So instead of 1 dozen, it's 1 mole, and 1 mole is equal to 6.022 times 10 to the 23rd. I think I only want you guys to memorize it to, 4 sig figs, okay? So 6.022 times 10 to the 23rd, okay? And that number is called Avogadro's number, okay? I'm going to switch over to the board. So we're going to um, do some example problems, right, to illustrate how to use mole, right, and convert between moles and items. All right. Okay. So, right, that's the analogy. Chemist dozen, right? So regular dozen, right, is 12 items, right? And items here, it can be anything, right? 1 dozen eggs be 12 eggs. 1 dozen oranges be 12 oranges. So it's just anything, right? So similarly, 1 mole of something is 6.022 times 10 to the 23rd. Okay, items. Okay. So let's do some calculations so you see how it works. Okay. Let's do it with dozen first. Okay, so let's say that uh, uh, I want to know how many eggs are there in 2 dozen eggs, right? So that's our unit, eggs, right? Um, so in 2 dozen eggs, how many eggs are there, right? So we have the true statement, 1 dozen is 12. And since we want eggs out, right, as the answer, we need eggs to be on top. So 12 eggs, 1 dozen eggs on bottom. So that dozen eggs cancel, right? Now you have 2 times 12 is 24. Right? And I mean, you could, you guys know dozens so well, you can be doing this in your head, right? But we got to show the work because trust me, you're not going to be able to do that in your head, right? So we have to say, okay, how do we arrive at 24 using that equivalency, right? Now we can go the other way around, right? If I have 144 eggs, I'm going to ask myself, how many dozen eggs is that? Okay. So you're going to use the same equivalency, but now you see that you need to put eggs on bottom so that eggs can cancel and dozen eggs on top because that's what you want for your answer, right? So now 1 dozen eggs is on top and 12 eggs is on bottom. Eggs can cancel. 104, 144 divided by 12, right? You see that it's 12 dozen eggs. Okay. So you see that in one case, right? We are multiplying by 12, right? And in the other case, we're dividing by 12, but we don't have to memorize that, right? Remember unit analysis, we don't have to remember when we need to multiply or divide. We just need to set it up so that our desired unit is on top and what we don't want cancels out, right? Okay, now I'm gonna do it with mole, okay? So you guys see exactly how it correlates, all right? So let's say, since in chemistry is when we use mole, let's switch over to, instead of eggs, we say iron, right? Atoms of iron. So let's say if I have 2.0 moles of iron atoms, and I want to know how many iron atoms that is. Okay. So what goes on top? What goes on bottom? Well, what is the equivalency? 1 mole of something is 6.022 times 10 to the 23rd of that thing, right? It's a lot bigger number than 12, but you apply it in the same way, right? So that means mole needs to go on bottom. So 1 mole of iron, okay? Atoms, you can even be very specific, right? 1 mole of iron atoms. And on top, that is 6.022 times 10 to the 23rd iron atoms, right? Because that's what you want out. Okay. So 1 mole of iron is you take 2 times that. Okay. So punch that into your calculator. You're going to get 1.2 times 10 to the 24. Okay. And by the way, guys, if you guys are having trouble entering in scientific notation to your calculator, this is the button that you need to be looking for. It's the double E button, and that stands for times 10 to the, okay? Or on some calculator, it's times 10 to the X or something like that, okay? But that's the button that you're going to be using in order to enter in these types of numbers, okay? So if you were to enter in 6.022 times 10 to the 23rd, this is what you should do. 6.022, hit the EE button, and then 23. Simple, right? 6.022 times 10 to the 23rd. That's all. If this was a negative exponent, then you throw in the negative. Okay, so very simple. Okay, so anyways, back to this problem, right? You guys see how um, this is analogous to each other, right? That's why we can think of the mole as the chemist dozen, right? Now let's do it the other way around. Let's say I have, 7.8 times 10 to the 24 atoms of iron. Okay. And I want to know how many mole of iron that is. So again, I'm going to do the line, right? Well, now this time mole needs to go on top, right? Because we want mole out. So you're gonna say 1 mole of iron is 6.022 times 10 to the 23rd atoms of iron. Okay, so atoms of iron cancel. And so let's do that calculation. 7.8 times 10 to the 24. Divide by 6.022 times 10 to the 23 is, and you want two sig figs here, right? Because of this number. So it's going to be 13 moles of iron. Okay, does that make sense? All right, so let's do a few more examples, okay? And we're going to use different units. So you guys can get really well versed with that, okay? But you yourself, you want to do a lot of these problems, right? So in this class, we're going to be doing that a lot, just, converting between moles and atoms or moles and molecules, okay? So that's really, it's one of the conversion factors that you're going to be using a lot in this class. All right, so let's do aluminum. How about aluminum atoms, right? So let's say we want, all these are dead. Let's say we have 0.145 moles of aluminum. Okay, right? Aluminum is the element, right? And a mole of aluminum, if we were to do this in dozen, okay, 1 dozen aluminum, right, would be 12 aluminum atoms, okay? Now we're asking 1 mole, though, of aluminum is how many atoms of aluminum, okay? So draw that division line, okay? Now figure out what goes on top, what goes on bottom, okay? First, we got to come up with an equivalency. This is equal to that, right? Don't actually start the problem until you figure out the equivalency, okay? And the equivalency is a true statement, right? So you have to clearly say, right? The true statement is 1 mole of aluminum is equal to what? 6.022 times 10 to the 23rd atoms of aluminum, okay? Generate the true statement first. And trust me, this is going to help you. Don't just start putting numbers randomly, okay? You need to make a statement, a true statement that makes perfect sense, right? In 1 mole of aluminum, that's 6.022 times 10 to the 23rd atoms of aluminum. Now, look at that and see what should be on top and what should be on the bottom. Well, we want atoms of aluminum out. So that's got to go on top, right? The number that's tied to atoms of aluminum has to go on top. Okay, and then mole goes on bottom, and that's just 1 mole, right, of aluminum. So mole of aluminum cancels out, right? Let's punch it in, and remember to use that double E button for your scientific notation. So I'm punching in 0.145, right, times, okay, multiply because this number is on top. Remember, you hit multiply when the number is on top. If it's on bottom, then you divide, right? So multiply 6.022 double E 23. And I get, all right, let's think about sig figs. How many sig figs do you guys think should be the answer? This is 4, right? And this is 3. So we'll go by least number of sig figs when you're multiplying and dividing. So we'd need 3 sig figs. 8.73 times 10 to the 22nd. Okay. 8.73 times 10 to the 22nd atoms of aluminum. Okay. Okay, let's do another example where we go the other way around, right? Just making up some numbers here, right? And you can do this too, right? you guys can do this to practice. Just make up some numbers or grab some problems from the book, and just practice. Okay, so now we're asking 1.65 times 10 to the 20th atoms of aluminum is equal to how many moles of aluminum? Okay, of course, we already have the true statement. Okay, all we have to do is figure out what goes on top and what goes on bottom. So we want mole out. So this time mole is going to be on top. Mole of aluminum is 6.022 times 10 to the 23rd atoms of aluminum. Right. So that cancels out. And now this number is on bottom, right? So you're going to hit 1.65 double E 20 divide by 6.022 double E 23. Okay. So number of sig figs, let's see, that's 4. Oh, that's 3. So we need to round to 2.74 times 10 to the negative 4. 2.74 times 10 to the negative 4 moles of aluminum. Okay, is that clear, guys? All right. Well, let's do another problem now, right? But we're gonna change it up. We're not gonna to from atoms to molecules, because sometimes you want to know about molecules, right? Let me erase this. Okay. So what if the question is, how many molecules of water are there in 5.4 moles of water? Okay. How many molecules of water are there in 5.4 moles of water? Okay. So we need to come up with an equivalency, right? That relates mole to molecules, because we know we need to convert between them, right? We're going from mole to molecules. Okay. So what's that true statement? Well, you know what a mole is. 1 mole of water, H2O, right, is equal to how many molecules of water? 6.022 times 10 to the 23rd molecules. Okay. Now earlier when we did Fe and Al, those were atoms, right? And so that's why we had atoms here. Okay, but here by context, water is not an atom, right? We know that water is a molecule. Okay, so you're gonna have to use context in order to see what should go here, right? Is it atom or is it molecules, right? But that's really, all you're gonna see in chemistry, right? Because that's what we talk about. Are we talking about atom or are we talking about molecules, right? So we have 5.4 moles of H2O, and we want to know how many molecules of water, right? That's the question. How many molecules of H2O? Okay, so again, applying that, right? Drawing that division line and then seeing what goes on top, what goes on bottom, right? And we already have that true statement. That's why we generate that true statement first, okay? And again, I want you guys to be doing that, right? Before you even start the problem, right? Now, what should go on top? Molecules. So this number that's tied to molecules is going to go on top. Molecules of water. And what should go on bottom? 1 mole, right? Because we want the mole of H2O to cancel out. Okay. So let's do it. 5.4 times 6.022 double E 23. How many sig figs, guys? That's 4. This is 2. So you're going to do 3.3 times 10 to the 24 molecules of water. Okay. Does that make sense, right? And let's start circling our answers too, right? To be clear. And this makes sense, right? I mean, this is a very large number, right? Times 10 to the 24th. That makes sense because we are asking how many molecules are in 5.4 moles, right? So you're gonna get a big number there, right? Now conversely, we can do it the other way around, right? We can ask how many moles of, and this time let's talk about CO2. How many moles of CO2 are there in 8.4 times 10 to the 25th molecules of CO2? Okay. Well, let's get the equivalency, right? Earlier we were doing water, so our unit was 1 mole of water. Well, this time it's CO2, so I'll just simply replace this with CO2, right? And the number is still the same, and it's molecules of CO2. You see? So it's that simple, right? And then we execute. Once we have the equivalency, start with what you're given here, 8.4 times 10 to the 25th molecules of CO2. And what do you want out? Moles of CO2. Okay, so division line. Now what goes on top? What goes on bottom? We want mole of CO2 out. So 1 mole of CO2 is going to go on top. On bottom, 6.022 times 10 to the 23rd molecules of CO2, right? So that cancels. 8.4 double E 25 divided by 6.022 double E 23. It's going to be 2 sig figs, right? Because you got 4 sig figs there and you got 2 sig figs there. So 139 is going to round to 140. Okay. Right? This 0 doesn't count. So 140 is only 2 sig figs, right? Only the 1 and the 4. Okay. All right. We're going to move on now to the next topic, but this is something that you guys need to practice, right? You see that we're going back between moles and molecules, and then molecules mole, right? So that's something that you guys want to learn, right? And do lots of examples. So go between mole and atoms / molecules, right? It's by context, right? You'll know if it's a single atom, then it's atom, okay? But that is the first very important conversion factor that you guys need to be able to do, okay? I'm going to teach you guys the second. It's a second conversion factor, and it's called molar mass. All right, let's go back to the slides. Okay, so molar mass. What is a molar mass? It's a way for chemists to count by weighing, okay? Because we can't see atoms, right? We cannot see atoms. We can't be like, oh, I need to do a reaction, but I need to grab, 1,000,000 carbon atoms and I'm going to start counting carbon atoms. We don't have a way to do that. So the only way we can actually count atoms is by weighing them, okay? And here's an analogy that, really illustrates how this works. Okay, so let's say that you guys are, you're working in a hardware store, right? And a truck full of nails just came in, okay? And your job is to figure out how many nails are in the truck that just arrived, okay? Now, you could count the nails one by one, okay? But that's going to take you all day, right? So, what's a more clever way to count? Well, by weighing, okay? So what could you do? You could take, one nail, right? and you can mass that nail and see how much it weighs, right? And then you can figure out the whole truck of nails, right? There's a way to put it on the scale, and you have the whole weight of the entire thing. And so then you can take that number and divide by uh, one nail's mass, and you'll have a number, right? So it's something like that, okay? But then you got to think, wait, perhaps, you know, maybe that's not the best way. There's even better way, because each nail is not made the same way, right? They're not manufactured the same way. So they're going to have slightly different mass. So what you need to do is actually get the average mass of one nail, right? So count out 100 nails, okay? And mass that, okay? And then take the total mass, divide by that mass of 100 nail, right? And then divide by 100 again. So you basically average out the small differences in each nail, okay? So it's something like that, right? Now, when you are measuring out atoms, it's similar, right? Because um, what you're doing is, the atomic mass, the little number that you see underneath the chemical symbol, remember, that was the weighted average of all the naturally occurring isotopes, right? So, in a way, that's what you're doing. You're averaging out, all the different mass of that element, right? All the different isotopes, right? They have slightly different mass, okay? And then what you do is, you use the mass of that atom to count it, right? So you go to the balance, and you can figure out how many atoms, carbon atoms, for example, there are by using the gram number, okay? So this is what we call a molar mass. The element's molar mass is in grams per mole. And that's a unit that I want you guys to remember, right? Just repeat over and over again, right? Grams per mole. So what does that mean? In 1 mole of this atom, okay, is this many grams. So let's look at your periodic table, and let's look at aluminum, right? Do you see that underneath aluminum, the number is 26.98? So that number is actually the gram number for 1 mole of aluminum. Okay, so 1 mole of aluminum is how much again, right? We just learned that it's this many aluminum atoms, right? 1 mole of aluminum is 6.022 times 10 to the 23rd aluminum atoms is equal to 26.98 grams, right? So we're counting by mass. So we go, if we know, we know that if we go to the balance and we put 26.98 grams of aluminum on the scale, we will have exactly this many aluminum atoms, right? 6.022 times 10 to the 23rd aluminum atoms, or 1 mole of aluminum. Okay, let's do it for another element. Everybody look at carbon and look at the number below, right? It's 12.01 grams of carbon for 1 mole of carbon, okay? Um, And again, that would be 6.022 times 10 to the 23rd carbon atoms, right? Let's go to helium. What's the little number below helium? 4.003, right? So that means in 1 mole of helium, it weighs 4.003 grams, okay? So now we can use, right, this equivalency, right? For example, 1 mole of carbon is equal to 12.01 grams of carbon. We can now put it, as a fraction to convert between moles and grams, right? If I have this many moles of carbon, how many grams is that, right? And vice versa. If I have this many grams of carbon, then how many moles is that, okay? So let's go back to the board, and we are going to um, do some example problems. All right, so this is our second conversion factor now, right? Going between mole and grams, okay, using molar mass. All right, so what if we were asked, and I'm going to do this example problem 2.7 on the slide there. It asks us to calculate the amount, let's look at it, right? Calculate the amount of carbon in moles, okay, in 0.0265 grams of pencil lead. Right. Of course, we know pencil lead is not lead, right? It's graphite. It's funny that we call it that. We obviously didn't know uh, chemistry back then. So it's not lead, right? It's just actually carbon. So that's why we're asked to calculate moles of carbon. Okay, so we know that we need to convert between moles and grams, right? That's the first thing you got to analyze when you're looking at these problems, right? What are the units that I'm converting between its moles and grams? And you're like, oh, well, what has moles and grams in it? Molar mass, okay? Okay, and literally that's what molar mass means, right? The mass in 1 mole. So you know that the unit is going to be grams per mole. So do it for carbon. What is it? Gotta make a true statement. Remember that. Don't even solve the problem until you have the full true statement. So you can say in 1 mole of carbon is how many grams of carbon? Well, where do you find that? The periodic table, right? All molar masses are on the periodic table. So 1 mole of carbon is 12.01 grams of carbon. Okay. Okay, so be specific. 1 mole of carbon is 12.01 grams of carbon. Now you're ready to calculate. So I have 0.0265 grams. I'm going to make a division line. And we are asking how many moles of carbon that is. Okay, so what's going to go on top? What's going to go on bottom? Well, moles got to go on top. 1 mole of carbon over 12.01 grams of carbon. Right? Grams of carbon will cancel. And we're going to punch in 0.0265 divided by 12.01. That's going to give us, and how many sig figs, guys? See, this is 4 sig figs. This is just 3, right? These zeros don't count. So I got to round to 3 sig figs is 2.21 times 10 to the minus 3 moles of carbon. Okay. All right. Let's do another problem. Back to our slides here. Okay. Calculate the amount of copper in moles of 35.8 grams of copper, which is Cu, right? So we want to know how many moles of copper that is. Right, back to the board. Okay, so we have 35.8 grams of Cu. Let me write that down here. It's a little bit of a glare. Okay, I'm going to make that line, right? That division line, 35.8 grams of copper. We want moles of copper out. Okay, so we got to come up with the equivalency, right? We need the molar mass of copper. Okay, where do we get it? The periodic table. What does it say? 1 mole of copper is 63.55 grams of copper. Okay. All right, so we need to put more on top, right? 1 mole of copper over 63.55 grams of copper. So 35.8 divided by 63.55. Okay, how many sig figs should we have? That's 4 sig figs. This is 3. So it's going to be 0.563 moles of copper. Okay. So key thing, right? Key thing is to get the equivalency first. Okay. Where do we get a molar mass? From the periodic table, right? It's that simple. All right, let's go back to the slides and continue. Okay, now it's asking us, how many copper atoms are in a copper penny with a mass of 3.10 grams? Oh, this is, let me rewrite it. This is more multi-step problem, right? Because now you're gonna see that we're gonna have to go all the way to atoms, right? So really nice problem here for us to practice that. How many copper atoms are in a copper penny with a mass of 3.10 grams? Okay. All right, let's solve that on the board. Okay, so in these kind of problems, right, you can see that it's not just a single step, because it's not just asking us to go from mass to mole. It wants us to go all the way to atoms. I always advocate writing out a plan first, okay? The plan tells you each individual step that you need to take to get to the final answer, okay? We obviously want atoms, copper atoms at the end, right? Because this says how many copper atoms. So that's copper atoms, okay? And we need to get to here. But where did we start? We started at grams, right? We started at mass. Grams of copper, okay? Needs to go to mole of copper, right? So this gram can go to mole through molar mass, right? And then from mole, you can go to atoms, right? Does that make sense? Okay. So now we execute once we have the plan, right? 3.10 grams. Do the line, right? And then we need the equivalency here. I would just write it right on top of my plan, so I have it there, right? How do you go from mole to gram? Use molar mass. So look on the periodic table, right? 1 mole of copper is equal to 63.55 grams of copper, okay? And then what is the equivalency for mole to atom? We just learned that one, right? On top. 1 mole of copper is, it's a grouping, right? Of how many? 6.022 times 10 to the 23rd atoms of copper. Okay, so now we can execute. First, we go from gram to mole. So we're using this equivalency. Mole's got to go on top. So 1 mole of Cu over 63.55 grams of Cu. Okay, and that cancels, right? Okay, and then next conversion factor. We're now at mole. We need to go from mole to atoms. So right now, moles is on top, right? We want atoms out. So we want atoms on top. That's 6.022 times 10 to the 23rd atoms of copper per 1 copper. Okay. All right, you see that? Are we two-step problem, right? So 3.1 divided by 63.55 times 6.022 double E23. That's gonna be 3 sig figs. So you're gonna have 2.94 times 10 to the 22nd atoms of copper. Right? Okay. So I want to summarize this for you guys, okay? This is a way of problem solving that you're going to see over and over again in this class. So you need to be able to master using these two conversion factors to answer, any kind of question, okay? So I call this the roadmap, okay? So let me show you what the roadmap is. It's a great problem, a way for problem solving, right? So it's a map for you to know, where do I start, where do I end, right? Now, in a problem solving, it's always asking for a question, like how many moles? That's where you end, moles where you end, right? And then there's always a given number. That's where you start, okay? So that's something that you need to identify right away. When you're reading a long word problem, right, that's how you orient yourself, right? Otherwise, you can't solve the problem. So the roadmap is a way, right, for you to be able to do that easier, right? Is to connect the steps so that it's, step by step, right? Because a lot of these are not just one step, the problems are going to get harder. You're going to have, multi-steps. And so the roadmap is a way for you to orient yourself, right? In order to solve the problems. So oftentimes we start at atoms and molecules of A, right? And we'll convert to moles of A. Now, we just learned about the mole, right? The reason why mole is a unit that's used in chemistry is because it quantifies an amount, right? Um, and so, and all roads you're going to see are going to lead to mole in the roadmap, right? Because when we're doing reactions, we want to know how much, right? We want to know amount. We don't want to know the mass. We want to know how many mole of that thing do we need in our reaction, okay? And so we go to mole a lot, right? Now, how is it that we go from atoms and molecules to mole, guys? Using Avogadro's number, right? Okay. But in which direction? Do you guys remember? We want to go from atoms, molecules to A to mole of A. We're going to divide, right, by Avogadro's number. Okay. You can, if you want to go back, you want a mole of A to atoms and molecules of A. Of course, then you're going to have to do the opposite, right? Okay. But I'm really spelling it out here because it's not something you have to memorize, right? Because you can just use unit analysis to figure out whether you're going to divide or multiply, right? That's why you write the true statement, and then you see which unit you need to go on top, okay? That you actually don't need to memorize this, okay? But I'm just really just spelling it out for you here. And then you can go to grams, right? For mole, grams of A, or back, right? Okay. So how do you go from mole to gram? Okay. Of course, you need a molar mass, right? But what do? You multiply by molar mass. Okay. So from now on, when you see me write big M, that's molar mass. Okay. From gram to mole, you're going to divide by mass of A, right? Okay. And where do you find molar mass, everybody? On the periodic table. Okay. So here we go. Let's do another problem. Last problem we're going to do for this chapter that utilizes the roadmap. So you guys see how that works. Okay. So now I can ask how many grams of CO2 are there in 7.2 times 10 to the 25th molecules of CO2. Okay. So in other words, if I have 7.2 times 10 to the 23rd molecules of CO2, that's a lot, right? How much does it weigh, right? How many grams is that? Okay. So remember, again, you're going to use, in these types of problems, you're going to do a plan, and you're going to use the roadmap to help you with the plan. Okay. So where do we start, guys? Molecules, right? We're given molecules. So we're going to start in this box here. Okay. And then it's going to ask us to go to grams. So we end at this box here. Okay. Grams of A. So that means we have to go like this first to moles of A and then down, right? So we divide by Avogadro's number and we multiply by molar mass, right? But again, we don't have to memorize that, right? Check how it's just, just really easy by using unit analysis to figure that out. Okay, so let's write our plans. Molecules of A is now CO2, right? That's A is anybody, right? So CO2, molecules of CO2, we need to convert to moles of CO2. And from moles of CO2, we go to grams of CO2. Okay. All right, so let's do that together. Okay. We start at 7.2 times 10 to the 25th molecules. of CO2. I'm not gonna have room. Let me erase the map for now. You guys have it, right? You're gonna have it in your notes, so you can be looking at that. But of course, the map won't be on the exam for you, right? So you're gonna want to generate that map, memorize that map, and then generate it, at the beginning of the exam or something. Just have that handy. I think it's really useful. All right. So 7.2 times 10 to the 25th molecules of CO2. Okay. Now let's think about the equivalency, right? Molecules to mole. Remember that? That's Avogadro's number, right? But write a true statement. 1 mole of CO2 is equal to 6.022 times 10 to the 23rd molecules of CO2. Okay. All right. So which one on top, which one on bottom then? Since we want mole out, 1 mole of CO2 on top, 6.022 times 10 to the 23rd molecules of CO2 on bottom. Okay, so that cancels. And then one last step, right? Next step is going from mole to grams. We need a true statement for that one, right? How do you go between moles and grams, everybody? Molar mass, right? The mass in 1 mole. Where do you find molar mass? Periodic table. Okay. Now for CO2, it's quite easy to find the molar mass. You know that the mass of 1 carbon atom is 12.01, right? Okay. Plus, you need 2 times the mass of oxygen. Okay. So you have all the masses of each individual atom. If you add up all the masses of all the individual atoms, you'll get, the mass of the whole molecule, right? So 2 times 16.00, we're going to get 44.01 grams per mole for CO2. Okay. So then our equivalency is in 1 mole of CO2, there are, right, it's equal to 44.01 grams, right? So get that equivalency going. Now you want grams out, so 44.01 grams of CO2 is on top, and on bottom is 1 mole of CO2. Okay, equal to, let's do this, 7.2 double E 25 divided by 6.022 double E 23 times 44.01. So sig figs 2, that's 2 sig figs here. These are 4. So we need to round to the least number of sig figs. It's 5.3 times 10 to the 3rd grams of CO2. Okay. That makes sense. All right. So yeah, we've done those 2 problems where we're doing multi-step, right? So you guys want to practice that too, right? Go find a problem where you go from molecules to gram, and then the other way to go around, right? Grams to molecules. So you just get used to using these conversion factors, right? This one and this one in order to do your problem solving, okay? Get really good at that because you're going to see it over and over again, right? Okay, that's it for chapter 2. I'm going to see you guys next time.